Okay, so let's resume. So the last 50 minutes or so, quick announcements before I talk about review, which is try to give some course evaluation feedback. Okay, it's useful to improve the program as we move forward for the especially the MSBA program. Okay. Yeah, and if many of you, I'm not sure many of you, but some of you have already registered for 576. But if people are unsure about 576 versus other options, drop me an email or talk to me or other faculty. People who want to be data scientists or that similar careers, then you would want to maximize your exposure to different types of methods. In addition to, of course, practical experience with trying out on real data. So 576 does offer that with unstructured data, which basically means images and text. So if you care about text processing, 576 is a good course. There are courses which are specific to text as well, potentially, specific to some specific other domains, social networks, and so on. So you should explore those options as you think about your data science journey. Okay, and if this is the last stop, that's fine too. Yeah. And yeah, so if I remember correctly, the exam is on 6th, which is next Monday. So the exam is going to be in the same room, and it's a 2-hour exam. And pattern in terms of time constraints, you hopefully should not have time constraints. And the number of questions would be similar to how it is in a midterm. So let's see, 6 questions. Okay. And so somebody was asking more sample exam questions. So who was asking? Murli, who else? You, and you asked by email. Okay. So several of you are asking more sample exam questions, which is fine. I mean, so more than sample exam questions, these notes that you have, or at least I'm providing, you should try to read them. You may not understand all the sentences depending on what your level is, but as I said, you should be definitely familiar with Introduction to Statistical Learning. So I have not been mentioning that quite a bit in my class, but it's kind of implicit that you have to pick, especially since this is not this is a fairly, solid start to a bunch of methods. You should have hopefully looked at Introduction to Statistical Learning. If not, I mean, of course, for some of you might have been following Elementary Statistical Learning. Okay, so if you have exposure to these 2 books, then you should be fine. And I know many of you have been looking at some of these, at least Introduction to Statistical Learning. So even concepts that we cover, we have covered post midterm, which is basically this list here, all the way from EM to clustering, principal components, to some tidbits on time series. Some of these topics are not there in Introduction to Statistical Learning, but majority of them are. So more than sample questions, you should be familiar with that. Or the simpler thing is to, of course, know what's there in the lecture notes. Okay, so definitely that I would bank on rather than sample questions, because I may give you some sample questions which should not appear in the exam, right? So in the first midterm, I have the question sheet. So yeah, I mean, so it will be calibrated. So we know how the performance was. So it will be calibrated to make it, if needed, easier. So don't worry about the I mean, the material is tough. I definitely concede. Like EM is not an easy topic. Similarly, principal components or even things like gradient boosting, they require some thinking to understand what's going on. So that's fine. So since the material is tough, try to do as much as possible in terms of basic reading. Like ISR books definitely should help. Yeah.
Is this a list of topics that it's going to cover?
So this is a list of topics. I mean, it is the same as what you have. It's like all the lectures. Yeah, this is a list of topics. Is this? But this there in the website. I mean, this is on lecture 12. So yeah, this is lecture 12. So that's why lecture 12 is short. But so this is a list of topics. So we'll actually go through some of these topics right now. So any other questions other than sample exam questions? Okay, did you guys find any topic too difficult? Has anybody started reading yet? Okay, so there's, of course, those informal videos should help you. They're basically repetitions, of the lecture. So if you missed a lecture or something, try to use that. Okay. Any topic? Yeah.
I thought Gibbs sampling was a bit insane. It was like very, very difficult.
Markov chain. So we have not looked. I mean, we only discussed the procedure. We have not looked at why it works in detail. If you're, I mean, we can cover why it works if you want. Yeah, that's one thing. Yeah.
Actually, can you explain once again MAP, MLE, log 0 to 3? I think all these concepts, whatever is there, the root, everything is related to those three.
MAP, MLE, and
Loss function, log loss.
Okay. So, okay, let me. So in the meantime, just think of which of the topics we want me to just revisit. But I also wanted to go in a linear way. But let's see. Let me answer these two. And so your question is a little bit easier. So loss function as a function of parameter is sometimes is relatable to maximizing the negative log. Maximizing the log probability of a parameter. It's typically beta itself, let's say, of a bunch of your random variable x, okay, or x comma y, or it could be, actually, to be more precise, y given x. Okay, if you care about okay, okay, let me repeat. So loss functions sometimes can be interpreted as maximizing the log likelihood, and loss functions with regularizer plus some constant times, like I said, 2 norm, can be so the same thing can be approximated or can be interpreted. So this squiggly sign, I'm saying interpreted as maximizing log likelihood plus maximizing log likelihood plus log prior on beta. Okay, so in the second version, actually, beta is a random variable, and in the first version, beta is fixed unknown, fixed but unknown. Okay, so MAP just corresponds to maximum a posteriori estimate. Just means that you want to consider both the likelihood of your data given the unknown parameter and your prior belief on the parameter. And because of the log operation, it turns out to be two additive terms. If you did not have log, then it will be likelihood times prior. Just remember the numerator for Bayes rule, right? Likelihood times prior. So MAP just means that you have this product. Can you find me the best? Can you find me that parameter value? If parameter is now a random variable, where this product has a peak. It's a distribution, right? So this parameter beta is now a random variable, so it has its own distribution. Ideally, we want to find the peak of the posterior, right? Somewhere this parameter takes the highest probability mass, but posterior is nothing but likelihood times prior. So we're just saying likelihood times prior, whichever is the where does the parameter maximize this right hand side of the Bayes rule. Okay, that's MAP. Okay, and you can keep changing. So this is a very generic statement, and you can change the definition of likelihood depending on the random variables. It could be Bernoulli, it could be Gaussian, it could be anything else. and this interpretation still makes sense. So parameter is random variable. I just want to find which part is this random variable taking a specific value. The assignment of the random variable has the highest probability mass. That's MAP. And maximum likelihood estimation is just a definition of the likelihood is just parameter is some fixed unknown parameter like beta. I use beta because for linear regression we have already seen beta. So loss would be literally y minus beta transpose xi squared sum over i's, right? So likelihood function in this case is we assume that y's are conditionally normally distributed. Okay, y is conditionally normally distributed given x. Okay, with mean being beta transpose x and covariance being variance being sigma square. Okay, while let's say y is scalar, then if you think of it as conditionally normal, then the log of some constant times e to the power minus something else, log and e to the power cancel, and so you have just a squared error, and that's what the squared error is. So minimizing the loss is the same as maximizing likelihood or minimizing the negative likelihood. Okay, so that's likelihood estimation, and that those two, so those three, MAP, MLE, and like loss functions are related that way. Not all loss functions can be interpreted as likelihood estimation. We have seen some losses, right? So for example, 0-1 loss, I'm not sure if there's a likelihood explanation for it. But the interesting thing which is relevant to us is sometimes maximum likelihood estimation is a hard problem. Okay, it's computationally difficult. It may have lots of hills and valleys. And so we use EM as a way to solve an MLE problem. Okay, so that's where we used Gaussian mixture model, two Gaussian mixture model, right? Where we had 5 parameters, mu1, mu2, sigma 1 square, sigma 2 square, and the mixture proportion. We kind of had these latent variables and unobserved variables of which component does each observation belong to as the additional data, and then did some sort of a 2-step procedure to maximize the marginal likelihood. So maximizing the likelihood on the data itself, we are doing it in a different way where we are finding the expectation or the probability that this latent variable takes, belongs variable which corresponds to which component the x's belong to. We first find what is the most likely component that the observation belongs to. So there will be n such variables. Once you get some likely assignment for them, or likelihood probabilities for them, then you use the M step where you maximize the joint likelihood of data, actual data that you have, plus this additional thing that you estimated. Okay, so your EM is a way to get to good estimation of the parameters of your likelihood function. Okay, so that's hopefully clears those three. We'll come back to EM maybe. For your Gibbs sampling, Gibbs sampling is, we wanted to sample, I think x1 to xp from a distribution between x1 to xp. Okay. Motivation is we cannot sometimes sample from distribution. So for normal distributions or uniform distributions, there's functions, right? So random or what a random, randant, those types of functions. But multidimensional functions, or even there could be some composition of like if you have two Gaussians and then you do Gaussian times Gaussian to the power 2/3. I don't know how to sample from that directly. Maybe if I have a nice generative description, by which I mean first get a Gaussian, second get another Gaussian, multiply them together, then maybe you can generate samples from it. But if there is no nice generative description, then it's a messy way to. It's not clear how to get samples. Okay. And if you don't know how to get samples, then maximum Monte Carlo Markov chain methods are the way to are one of the popular ways to get samples. Okay, and they work on the principle that that you should be able to sample from you should be able to trade off independence. So you may be able to create dependent samples such that like I want to get samples from this. So let's say xi. Basically xi I is equal to 1 to n are samples that I want to draw from this distribution P. Okay, where this is P. Xi's are in Rp, right? P dimensional vector. If you think of feature vectors, okay. I want to get these samples, n samples. They're not dependent. I want independent samples. Okay, that was my ideal goal. I'm saying that it's maybe difficult to get the samples. So let's actually trade off something which is like create correlated observations such that in some way such that I'm actually getting samples as if they are from the target distribution, this P, this P. We're introducing correlations. That's through the notion of some sort of a Markovian angle to it. So you have to make the next sample dependent on the previous sample, and we have seen an example today, right? We had this Markov thing where WT dependent on WT minus 1. Similarly, in Gibbs sampling, getting an observation like a row of your n observations depends on what were the values of the observations before. Okay, so that's a way to get these samples. Now, so before I get into why does Gibbs sampling work, I'll just quickly in one sentence tell you why, what's the procedure. The procedure is you need to have access to the conditional probabilities of finding x, let's say 3 dimensions. So P is 3, let's say. So I need to know probability of x2 given x1 and x3. I need to know probability of x3 given x1 and x2. I also need to know probability of x1 given x2 and x3. Okay. So if I knew these 3, then there is a computational procedure, which is sample x2, sample x3, sample x4 in certain way. Okay. To construct my whole observation, from which I can construct my next whole observation. Because there is dependence over here, I need to know x1 and x3 to get I need to know x1 and x3 to get x2. But while getting x2, x3 is not generated, so I'll use the previous observations x3. So there is some relation, so there is some dependence. Okay. Now, why does it work? Okay. Whatever this black box is, so I said, so we want to go from x1 observation, x2, x3, all the way to xn. Let's say we want to create these guys. We can't sample from each p of x independently. So what we do is somehow create a box, some sort of a way from going from x1 to x2, which is dependent. So while creating x2, I use some information from x1. That's a dependence. That's a Markovian dependence, which is basically p of x2 is equal to x2 given x1 is equal to x1. Okay. In general, it's going to be p of xi is equal to xi given xi minus 1 is equal to xi minus 1. Okay. So this box essentially is supposed to let me get these types of samples. Okay. So that's the Markovian dependence. Now, a nice thing about such certain Markovian distributions, certain Markovian distributions like this. Okay. So this box is supposed to implement something like this. It will have its own parameters. Okay. The nice thing about this guy is that you can choose certain types of these conditional probabilities, because this has not been told to you, right? You only know p of x. That's just a marginal probability. Nobody told you p of x given some other x. Okay, so you are constructing it yourself. Okay, some arbitrary relationship between xt minus 1 and xi minus 1 and xi. So I'm constructing something. Gibbs sampling constructs a specific version of this box. Okay, such that this conditional probability. So if you keep sampling from this conditional probability, you get samples from p of x. In other words, this conditional probability corresponds to what is called a Markov chain. Okay, Markov chain just means it's just determined by what's the next sample, what's the next value given the previous value. Okay, so this is nothing but the same as Markov chain. Okay, now this Markov chain has what is called a stationary distribution under some nice properties, but just think of it as, don't worry about the nice properties, but this Markov chain, all Markov chains, many good Markov chains have this notion of a stationary distribution. Okay, which just means that after long enough samples jumping around this Markov chain, think of Markov chain literally figuratively as some bunches of what are called states, or in this case any of these random variables. There's going to be transitions from each these are called states. Okay, there's going to be a bunch of transitions. There's going to be transition probability. So that's what it means. So p of x2 given x1 just means that let's say I'm here. What's the probability of me going here? What's the probability of me going here? What's the probability of me going here? Okay, that's what it is. Okay, so think of jumping around this Markov chain. It turns out that if you many good Markov chains have this property that if you keep jumping around, there's something called a stationary distribution. Okay, the stationary distribution is a distribution which as if essentially interpretation is just that if you jump around the Markov chain too long, then if you look at a signature of like the samples that you got, you jumped around, you observed what all values you got. If you look at those numbers, you look at the histogram, that looks like the histogram of the histogram of that looks like it doesn't change over time. That's why it's called stationary distribution. But for Gibbs sampling, we construct something clever, that box over there, such that the stationary distribution is actually p of x. So in Gibbs sampling, what we are just doing is that we don't know what we can't sample from p of x, but we'll create this object, star marked object, which happens to be this these based out of these three guys. But whatever that is, that star marked object is such that its stationary distribution happens to be p of x, which is the distribution we care about. Okay, and generally Markov chains, as I said, have stationary distributions, which just means that if I keep jumping around the Markov chain, after a long time, if I look at the histogram of these what values I'm taking, okay, they don't change over time. So if I look at a bunch of next 100 observations, they have some histogram. Next bunch of observations, they have the same histogram. Okay, that's called a stationary distribution. And Markov chains have that property, and we are creating a Markov chain which is what Gibbs sampling is, specific Markov chain for which we are getting samples from p of x.
When you start problems like this,
yeah.
Do you start with data, or do you start with the distribution shape, or what?
So Gibbs sampling, you are asked to explicitly sample from a distribution. So somebody tells you. So for Gibbs sampling, so what is the requirement? You need to know these conditional probabilities. Okay. In fact, you don't even need to know. Somebody doesn't have to tell you what the joint distribution of p of x is, like this p of x1 to xp. Nobody has to tell you, but people have to tell you how to get all sorts of conditional probabilities. What is the conditional probability of x2 given x1 x3? What is the conditional probability of x3 given x1 x2? Somebody has to tell you. Okay, maybe the first guy is a Gaussian, next guy is a Bernoulli, third guy is a gamma distribution, whatever. Okay, somebody has to tell you that. Okay, once they tell you, then you just computationally just get samples from each of them in some sort of a round robin manner. It just means one after the other keep generating, okay, and concatenate p numbers, and that's your observation. So that's the computational procedure. Computational procedure is easy. Somebody has to give you access to these function calls, basically, or these conditional probabilities. Okay, some lookup tables, and that's it. So you generate the samples. The samples have a nice property because these three, in this case p is equal to 3, these three somehow together specify a nice transition probability matrix, or transition probability, whatever that object, conditional probability distribution. Okay, that's also called transition probability distribution, whose limiting or whatever the stationary distribution happens to be the distribution of your interest. So you cared about sampling from the distribution of your interest, but we constructed a Gibbs sampling procedure whose limiting distribution is the distribution of your interest. Okay, so that's like a roundabout way of getting samples from our distribution. Okay, I don't know if that explanation helped, but I know it's hand waving a little bit, quite a bit. We can discuss more after the break, afterwards. Okay, any other question? Okay, so let's look at the sequence of topics in a linear manner, okay, to see where. So in lecture 7, we looked at EM, and we looked at EM in the context of two Gaussian mixture model. Okay, in general, it also works for multiple components, and not just for Gaussian mixture models. It also works for. So how many of you have heard of latent Dirichlet allocation, like topic modeling? Okay, so topic modeling is a way to like do unsupervised learning on a bunch of text data. Okay, we study that in 576 and maybe other courses. So again, there also it's essentially some sort of a likelihood estimation problem, which is hard, and so you will use EM to do that likelihood estimation. Okay, that's an example of a practical method which is used for topic model, text processing, where you use EM. So Gaussian mixture models, as we said, are also used for clustering. So if there's a question in the exam, it says what's the generative way to do clustering, then you should know Gaussian mixture models are a way to do clustering. And then if I ask you like what are the ways to how do you estimate the parameters of a GMM, then EM is one way to estimate the parameters, right? I mean, you can of course say computationally I'll directly write the marginal probability distribution and do some gradient descent. That's also fine. Okay. So those are the applications of EM. Okay, two examples that I just mentioned. I mean, things which are not there in notes, you don't have to give as examples and so on. So LDA, don't worry about it. Sorry, latent digital allocation, don't worry about it. So in this in this section, you want to understand what the E step and M step are doing. Okay, so an intuition for like what is E step? E step is doing something about data that was not observed, so which I have assumed in my model, but data not observed. But once I know something about the data not observed, in the M step I care about the joint likelihood of the data observed, data not observed, the joint likelihood of them. I'm maximizing I'm figuring out the parameters, maximizing that likelihood. So at that level, you should be sure what's going on. Okay, and of course, connecting back to I think lecture 10, you should, or was it 11? 11, I guess. So what's the relation between EM and Kmeans? Okay, so there is some similarity in terms of the Kmeans estimating the cluster centers given the cluster assignment, and finding cluster assignment given the cluster centers. So there's some similarity, okay, in the EM and this K-means steps. So you should know that connection. In the notes, there's also derivation of why EM works, but you should just know that conceptually. You don't need to derive it. No derivations in general. Okay, so don't spend time on like preparing derivations like which are more than 4 equations long. Okay. Yeah, sampling. There's a little bit more information about sampling in the notes. For example, how do you sample from how do you sample a PMF? Okay, so you have a probability mass function. Okay, let's say it's a probability mass function which takes value 2, 3, and 4 with probability 0.3, 0.3, and 0.4. Okay, so this is a random variable which takes 3 values with these probabilities. Okay, then how do you get a sample from this? If I tell you only have access to a uniform distribution between 0 to 1. Okay, this is so this I don't know if the notes, I think the note explains this. I'll have to check, but for example, if you want to get a sample, what you do is break that unit interval into 3 parts, okay, of length 0.3, length 0.3, and length 0.4. okay, and just draw a uniform sample. So maybe it's over here. Okay, then you say that my sample is 2. Maybe if it's in the second region, just say your sample is 3, and in the third region, just say it's 4. Okay. That's a way to get a sample from this PMF if you only have access to the uniform distribution. Okay, now you have to, so just accept that as fact for now. I mean, let's not go into detail, but think about it conceptually why this makes sense in terms of generating a PMF with that probability mass 0.3, 0.3, 0.4, 2, 3, and 4. The 2, 3, and 4 are just random symbols. Okay, doesn't matter whether it's 2, 3, and 4 or 10, 20, and 30. But why me sampling uniform and from me sampling uniform distribution, and if it's between 0 to 0.3, assign it as the first number 2, and why if it's between 0.3 to 0.7, 0.6, assign it as symbol 3, makes sense. Okay, I mean it's not very hard. The hint is that when I'm sampling from 0, sample a uniform distribution, and if I get it from 0 to 0.3, then if the probability of me getting a number between 0 to 0.3 is exactly 0.3, right? So if I get any number, and if it happens to be between 0 to 0.3, the probability of that number is 0.3, and the probability of my first symbol is 0.3. Okay, so if I get any number there, and if I say that it's now number 2, then I have effectively done the same thing. Okay, so that's a very quick hint, but think about it. And there's some little bit of discussion in the notes about what Gibbs sampling does, so definitely look at what it does. Okay, and then I think generalized iterative models is just some definition of, you can generalize, you can have more interactions, or you can have this link function, which is not difficult to read. Okay, any questions about that chapter? I think I went a little bit slow, so So next, tree-based methods. Many of you are familiar. Some of you are quite familiar with it because you have actually done assignments on this in some other classes, right? So tree construction, just be sure like what you're doing, right? Well, you're splitting two regions. What are the different criteria? I mean, I don't want exhaustive lists of like what does gene index mean, or what something else, misclassification error means. That's not important. Like what types of splits are possible. So what happens in random forest, right? You're going to subselect a variation of random forest. You're going to subselect the features you're going to split on, right? So that you should definitely know, like what is meant by subselection. If I like specifically say, okay, this feature 1 is income, feature 2 is something else, feature 3 is this, give me an example of what type of split you would do in a random forest construction, like a tree construction. Then you should give me an example using these specific names that I gave you. Okay. So I mean, just be familiar with be able to state what if you know what how does random forest different from bagging and a single tree, then you'll be able to answer this. Okay. So things like so there are some additional details about things like what happens when there are too many predictors. Then do you spend like there are a bunch of predictors, sorry, not too many predictors, some predictors which are categorical, some predictors which are continuous. Then what do you do with it? There's no complex answer here. It's just that, okay, if there are categorical variables, then maybe there's a certain way to split them. Maybe they'll take up too much of my split choices. Like maybe there are too much split choices which are about the categorical variables only, because there are so many choices to consider. So just read this categorical predictions on page 6, and you'll get some idea. Okay, so that was tree methods. And then actually tree methods chapter also has one key framework, forward stages, additive models, and we saw boosting, but in general, boosting, add a boost. There's some discussion about why AdaBoost fits into like this forward stages additive modeling world through this notion of an exponential loss function. Okay, it's fine. I mean, so just have a light reading of that chapter. So I'm not going to ask you derive exactly some equation or something. So because the AdaBoost itself has some specific functions that you need to compute, and we don't need to know those details. I mean, if there is some question on AdaBoost, I'll probably give you what that function is, like the error function that I see in the notes. Maybe I'll just give it to you. Okay, you don't have to memorize that, but you need to understand like what's happening conceptually for AdaBoost, right? So there's a reweighting of there's an additional weights. So it's called cost sensitive classification essentially. So you are adding weights in front of loss function. So instead of doing sum of yi minus xi transpose beta square, you're doing wi times 1 by sum of wi, maybe whatever it's equal to something like this. Okay, this is this cost sensitive classification, and AdaBoost essentially will probably do this is what the weights of the AdaBoost essentially would do. I mean, AdaBoost itself it doesn't specify how do you train. Okay, it just says fit a classifier, but this is what weighted classification essentially means. And in additive models, there's of course gradient boosting. Okay, so just read the discussion about why we went towards gradient boosting in the notes. There was some difficulty in adding models, especially if they are trees. They're not differentiable. Okay, you can't just do argmax. You can't just easily fit a additive tree model in a nice way. You could, it's computationally expensive, but gradient boosting gives you a certain way of intuition that adding models, adding a new tree is like fitting on the gradients gradients at the current point in terms of, so if you have already m-1 models, okay, m-1 trees, okay, then find the gradient of your loss function at the m-1 trees evaluation at the in the n-dimensional space. Okay, So there'll be n numbers, gradient values. Then think of those as targets and fit a new tree in a greedy manner. Okay, that's a very high level idea. So at least the idea you should be familiar with. I mean, there's no theoretical analysis for why gradient boosting is the best method or anything, but that's how it kind of fits under this forward stages additive modeling family. Okay. Any questions about that? So there's a slight difference between gradient boosting for regression and classification. Okay. As well as, of course, there's a slight difference between tree construction, classification, regression. So you should know what the slight difference is. Okay, so next let's look at random forest and bagging. So random forest is, I mean, it's just half a page here. So so in that next lecture 9, so basically there is this notion of variable importance. You should know whether variable importance is only applicable for random forests, or can it also be used for, let's say, a cart, right? Try to think about it, whether it's applicable for both. Similarly, so Mars is just an example of a nonlinear, greedy or a forward stage-wise additive model construction. Okay, so I wouldn't ask the details of the construction for sure. Okay, but that doesn't mean you don't read it. For example, I may ask what is the hinge function, so you should know what a hinge function is, right? You guys are taking notes for this? Okay. I can upload the video, I mean the screencast sometime. So in SVM is an important idea because it's motivated in a different way. I mean, you can directly motivate it as like a hinge loss function with some regularizer, right? Then we wouldn't have to deal with margins and all that. So you need to understand like the margin point of view of thinking about, first of all, binary classification in a separable setting, and then how do you kind of deal with real data which is generally not going to be separable. Okay, and if, for example, there could be a crazy question like, can you use SVM for 3-class classification? Then you will have to think of whether it is applicable or not, and answer. Okay. So any questions or concerns about this chapter? I mean, SVM and the idea of margins is kind of important, and and random forest and bagging is just simple definitions.
Yeah, I have a question about SVM.
Yeah.
For your cost parameter C, if you increase that, how does that affect your variance and bias? Like the higher C is, the harder the margins are, right?
Higher the C is,
the higher your penalty for violating the margin. It would seem like the less violations there would be, right?
I actually don't know. So let's see. Higher the C.
Misclassification.
Higher the C, I think it's
Lower the margins, like the margins would be contracted.
higher the C, you are not willing to give too much slack. Okay, so the margin area would be like very close to the decision boundary. So if you think of a hyperplane, just like high C means like really squeezed in dotted lines, and the dotted lines just represent like a margin gap from that hyperplane.
Because of that, would you be more likely to overfit, or would it be the other situation where?
Would you more likely to overfit? Good question. So actually, there's a good illustration in the notes, right? So let's look at it. So it's not clear to me, but maybe you can answer. Where is it? This is what, lecture 10. So if you look at this diagram, so this diagram is, the top one is for C is equal to I guess 10,000, and the bottom one is for C is equal to a smaller number, 0.01. So I mean, we had the right interpretation, but the question is which one is overfitting. First of all, both are underfitting like crazy, because the decision boundaries, at least in these two pictures, is like highly nonlinear. So already these decision boundaries are underfitting, right? They are not capturing the pattern in the data. So I mean, I guess these pictures are not useful for answering your question.
It depends on data as well. Like we cannot be very sure about it. Like, we have to test different values and then maybe do a cross validation as well to check how it is doing.
That is fine, but that's not a very satisfactory answer, I would say. But so think about, like, put a few points, like 4 points, and see what happens. Like if you have high C, are you willing to tolerate points getting inside the margin or not? Because the points getting inside the margin is when you start giving slack being positive. Okay, so if high C, then you don't want that to happen. Then there will be a certain hyperplane which will which would be like look ideal in your diagram. But if you have really small C, then you're willing to give some slack. So maybe you're willing to have a lot of points crisscross each other and so on. So just think about it, but I don't have an answer right now. Yeah. Any other question about SVMs? No.
So about SVM also, there was this one question which I had asked that it falls into parametric or non-parametric models.
Yes, it is parametric, right?
Yeah, but then online there is a discussion that when you are using kernel-based SVMs,
yeah,
those are basically non-parametric, but your linear SVM is parametric.
Yeah, I mean, so remember the kernel. So we jumped. So we are no more in 9. Okay, we are in chapter 10 or lecture 10. So kernels are a way to be non-parametric. So kernel, we don't specify the phi function, right? So if you specify the phi function, okay, lecture 10. So k of x prime is phi of x, transpose phi of x prime. So if you tell me the phi, then it's like a parametric model. Okay. So when you directly specify k of course has, so by the way, non-parametric methods also have parameters. Okay, so it's a misnomer. So the kernel function, for example, can have parameters, whatever, gamma and stuff like that, if it's exponential smoothing kernel, Gaussian kernel, whatever. So in the linear kernel case, this is just x transpose x. Okay, x transpose x prime, whatever.
And basically these also become your parameters, these transformations, right? And it will grow if you use kernel method. So like the answer which I found online was that.
No, I mean, phi is a pre-processing construct. I mean, so in the sense that if you're using a kernel, that implicitly specifies some phi function. But in general, kernel methods, you can classify them as non-parametric objects in the sense that they don't directly talk about this pre-processing transformation.
There are not limited number of parameters. There are infinite parameters in kernel methods. That is what will happen.
Where do you see the infinite number of parameters here?
No, because in the data, what will happen is that
no, I mean, there is no data here. So are you saying that this is infinite parameters or finite?
I'm not saying, but when you apply a kernel SVM on a data set, you are basically kind of taking dot products between data points. So it will grow exponentially if your data is growing. So there will be infinite number of parameters for your model.
No, that's we need to discuss this offline. But see, kernel methods are in general, even SVMs. I think there's a picture here. They're letting you push your data into high dimensional spaces. Okay, so even infinite dimensional spaces. So the data points themselves, the data points here are in 2 dimensions. Okay, think of a phi transformation pushing them into 5 dimensions or 10 dimensions. In a 10-dimensional space, you're basically thinking of a linear classifier in the 10-dimensional space. That, when you project it back, is like this. Where is this? This black curve here. Okay, the 10-dimensional linear classifier is in 2 dimensions, looks nonlinear. Okay, and it kind of better approximates this this purple curve, which is the actual decision boundary in this case. Okay, so kernel is just kernel methods or kernel trick is letting you do some classification in a different space, although you're not directly accessing that space. Okay.
The algorithm doesn't go into that. They just do some calculations in the lower dimension only. They never project it to higher dimension. Like
how is this point adding to my conversation?
Because this is something which I was talking about, the parameters. Like
no, let's discuss that offline. Anyway, so but kernel trick is important. So understand what's happening with the kernel trick. And what else is there in lecture 10? So what are support vectors? I think that's a standard question. Most of you might have seen it. But you need to understand that in terms of this slack. Okay, so there are some points where there is slack. Slack is tight in the sense that inequality, constraint inequality is tight. Okay, what does tight mean? Just means that the inequality is equality. So just be aware of that. And in this lecture 10, there's also association rules. So so at least nuances of a priori. So for example, what if the minimum support is 0? Okay, what if the minimum support is 0? Then how many sets would how many frequent item sets would a priori produce? Okay, what do you guys think? The minimum support is 0. Then how many sets would a priori produce? Just think about it. What if the minimum support is 1? Okay, then how many sets would a priori produce? Think about like what happens in these cases. Okay, so for example, if a minimum support is 1, then the moment you have a data set where all transactions are not the same, you will not get any frequent item set. But in a data set where all transactions are the same, then you'll get that particular transaction as your frequent item set. Okay, when minimum support is 1. Just just corner cases. Think of for really small, like 2, 3, 4 observations, three items. Okay, just think of like just fill in some table like that and see what happens when you choose minimum support to be 1 or 0, and you'll get a feel for like this question. I mean, I just made this question on the fly, but these types of, you need to have some understanding of a priori like this, or in general what frequent item sets are and what minimum support means. Okay, that's 10. Any questions about 10? Lecture 10. Okay, so association rules. Also the mapping from, what's the difference between rules and frequent item sets? So there's some relation, right? So you need to be familiar with that. Lecture 11. So it's unsupervised learning. So basically, K-means. So definitely the difference between K-means and K-medians. MEDIO-ID. What is the spelling? OIDS. DOIDS. Anyway, so there is so for example, like what's the difference in the inputs for K-means and K-medians? You should be able to answer. That's an easy question. What if I ask like what is the computational complexity? That may be a tough question, but in between would be the types of questions you can expect. Okay, like for example, K-means, can I change the distance function to something else? Okay, it probably can be done. So you should not be stumped by, oh, what if I don't use Euclidean distance, but what if I use weighted Euclidean distance or something like that? It should be still fine, right? It's just a distance. So that's K-means. Next, principal components are in general. Actually, in principal components, you should know what principal component directions are and what principal components themselves are. It's some sort of, in this notes, it talks about like some dimensional reduction point of view of the thing, where principal components in q dimensions or smaller number of dimensions, 3 dimensions, are like some sort of a linear projection of these higher dimensional points. Okay, such that high variance directions are preserved. High variance, directions are preserved. Okay, so we did some derivation on what was variance and why was it high. We don't need that derivation, like you don't have to do it in real time or anything, but you should know like what is an SVD for sure, because that's an important component of getting the principal components, right? So and also like what is the order relationship between the singular values and eigenvalues appropriately. Okay, so and then spectral clustering. A part of it is just K-means on something, right? But the example I was trying to give in the class about if you had these 3 circles, right? I mean, there's a picture in the notes in lecture 11. Like, why would Kmeans fail, and why would what is it in this top left picture? Why would Kmeans fail, and why would spectral clustering may succeed? So at least an intuitive idea of like why it would happen, like, right? That would be a good, I mean, good enough. If you can understand that, that's good enough for this part, I would say. Okay, and that's it. That's lecture 11, and 12 we just covered too. We are not gonna do a review of that. Yeah. So any other questions about the course? Okay, so closing remarks. It was we looked at supervised learning for majority of the time, linear models for a long time. Then we looked at a couple of lectures on unsupervised methods, and then again a little bit on time series and a few other tangential things, like not tangential, but things did not fit into the original storyline, like EM and maximum likelihood, bootstrap, and so on. But this is like this is the foundation. We have spent a lot of time on methods, but in reality, if you go to projects, 90% of the time is spent on getting your data to a state where it's very obvious what to do. Okay, so which we have not really spent time on, except for, of course, in the assignments we have tried to work. I mean, but those data sets were already prepared. Okay, so so when you have messy data, you have to most of the time is spent on getting the data to a good level. But if you know the methods, then you know where to get to. If you don't know the methods, you will do a lot of ad hoc things, and the inferences are kind of you may fall short of the full potential that you can extract from the data. Okay, so we spend so typically courses are methods heavy because they need a little bit of more careful thinking. But at the same time, when you finish the course and during summer, try to do some data munging. Get some data sets from online, from Kaggle or wherever. Maybe you should take up summer challenges. Participate in a Kaggle competition or something like that. Okay. So hopefully I'll see you in future ML courses, machine learning or statistics courses. Thank you.